Hello everyone, in this video we will cover the section 2.1. In this section we will see matrix operations. If A is an m by m matrix, this is the size of the matrix, which means that a matrix with m rows and n columns, then the scalar entry in the ith row and jth column of A is denoted by little aij. You see the notation, and it is called the ij entry of the matrix A. So you see the general notation for a given matrix. We have m times n entries for this matrix, m times n entries. And another notation is theoretically written as aij, to write shortly m by n. When we talk about a matrix theoretically, so generally we use this one, and sometimes we can write the most general expression for a matrix like this one. And when we want to state the general notation for the entry of the matrix A will be written as aij. Okay, it means that it is an entry of the matrix A in the ith row and jth column. Okay, the first number states the number of rows and the second number states the number of columns. As you can see, now we are in ith row and first column. The second number is the number 1. We are in the first column. Okay, and for example, for 3 by 3 matrix, let's write A11, A12, A13. Namely, we are in the first row and first column, second column and third column. A21, A22, A23, which is the second row, and A31, A32, and A33. So this is the clear expression of a matrix whose size is 3 by 3. For example, this entry is in the first column, which is corresponding to the second number, and second row. Okay, second row. So each column of a matrix A is a list of m real numbers, which identifies a vector in Rm. Okay, in Rm we have m components for each column, as you can see. Generally, for the general statement of the matrix A, we have m components, which means that each column identifies a vector in Rm, since we have m entries in each column for the given matrix. Therefore, every column is corresponding to a vector denoted by bold A1, Aj, An. Okay, so on. Therefore, another notation for a matrix is given in this form. A1, A2, blah blah, An are the columns of the matrix A, you know, from the chapter 1. And each column has m components, as you can see. For example, we want to write clearly the components of the second column, which is the vector in Rm. So the components will be A1, A12, we are in the second column. The second number should be always 2, and we are in the first row, A12, A22, and A32, and so on. The last one should be AM2. Okay, So this is the second column of the matrix A, whose size is m by n. M by n. So the number aij is the ith entry from the top of the jth column vector ag, as I said now. And the diagonal entries in n by n matrix, this is the theoretical notation you see, are a11, a22, a33, namely the number of rows should be equal to the number of columns. They are equal to each other, as you can see. So they are called diagonal entries, and they form the main diagonal of the matrix A. And the diagonal matrix is a square n by n matrix. N by n matrix whose non-diagonal entries are 0. N by n matrix. N by n matrix. Diagonal matrix is a square n by n matrix, namely the number of rows should be equal to the number of columns. It should be n. For example, 2 0 0 0 1 0 0 0 minus 5. So this is 3 by 3 square matrix. Square matrices have the number of rows which are equal to the number of columns, namely they are equal to each other. In this case we say this matrix as a square matrix. And a diagonal matrix is a square n by n matrix generally, whose non-diagonal entries are 0, like this one. We have non-zero numbers on the main diagonal of the matrix A. This is the main diagonal of this one, 3 by 3, A11, A22, A33. A11 is equal to 2, A22 is equal to 1, and A33 is equal to minus 5. And all entries except the main diagonal are zeros, which means that this is an example for the diagonal matrix. Okay, this is a diagonal matrix. Diagonal matrix. An example also is the n by n identity matrix, IN. Namely, all entries on the main diagonal will be 1. For example, 3 by 3 identity matrix can be given as 3 by 3, 1 0 0 0 1 0 0 0 1, or 4 by 4 identity matrix can be given as 1 0 0 0 0 1 0 0 0 0 0 1 sorry 0 0 1 0 0 0 0 1. As you can see, all entries on the main diagonal are equal to number 1, and all entries except the main diagonal are 0. So these matrices are called identity matrices. Okay, and generally it is denoted by IN. For example, I3 by 3 also can be written as I3, and this is I4, and so on. Okay, this is an important example for diagonal matrix, and you see another example here. And n by n matrix whose entries are all 0 is a zero matrix, is written as 0. Okay, zero matrix can be given, for example, in R cube, namely all entries are equal to 0, like the 0 vector. Okay, all of them will be 0. Two matrices are equal if they have the same size, the same number of rows, and the same number of columns, and if their corresponding columns are equal, which amounts to saying that their corresponding entries are equal, which means that all entries should be equal to each other for two matrices in order to say that they are equal. Okay, each entry for them has to be equal to each other. If A and B are n by n matrices, then the sum of them is again an n by n matrix whose columns are the sums of the corresponding columns in A and B. Since vector addition of the columns is done entry-wise, each entry in the addition of the matrices is the sum of the corresponding entries in A and B. Just we will add the corresponding entries of the given matrices to compute the addition, the matrix addition of the given matrices. Therefore, the sum of these matrices is defined only when A and B are the same size. Okay, we have to have matrices whose sizes are same. For example, A is 2 by 3 matrix, 2 by 3 matrix, B is 2 by 3 matrix, and C is 2 by 2 matrix. So let's find A plus B and A plus C. Just we will add the corresponding entries 4 plus 1, which are the first entries in the first column, will be 5, as you can see. And when we look at the second entry in the first column, we have -1 and 3 for the given matrices. So the addition of them will be 2, which forms the second entry in the addition in the first column. And 0 plus 1 is 1, 2 plus 5 is 8, 5 plus 1 is 6, and 2 plus 7 is 9. Okay, so we can apply the addition operation for the given matrices since we have the same size for them. They are 2 by 3 matrices, as you can see. But when we talk about the addition of the matrices A and C, so it is not defined because A and C have different sizes. C is 2 by 2 matrix, but A is 2 by 3 matrix. We have additional column here. We have 3 columns here, but here we have 2 columns. Therefore, we cannot do anything for the last column, which means that the addition is not defined for them. If R is a scalar, this is another matrix operation, and A is a matrix, then the scalar multiple R times A, written here, is the matrix. Again, we have a matrix whose columns are R times the corresponding columns in A. Okay. For example, we want to multiply the addition of the given matrices in the example by 2. We want to find 2 times A plus B. So we have just we multiply the entries of the addition by 2. So we have 10. 4, 2, 16, 12, and 18. That's it. This is the matrix operation called scalar multiplication. After understanding the definitions of addition of two matrices and the scalar multiplication of a matrix by a number, we have some basic properties for them. Let A, B, and C be matrices of the same size. Let R and S be scalars, namely numbers. So we can change the places of the matrices when we apply addition for them. The order is not important in addition operation, as you can see. When we find A plus B, also we find B plus A. They are equal to each other. Okay, we can change the order of the matrices when we apply addition operation. And also we have associativity property for the addition of matrices. As you can see, the place of the parentheses can be changed, as you can see. First you can apply addition for A and B and plus C, or first you can apply B plus C, you can find B plus C, and then you can add the matrix A. They give the same result. Okay, we can change the place of the parentheses when we have three matrices for the addition. And A plus 0 is equal to A, you can see easily. And we have the left distributive property for the scalar multiplication, which means that the number R can be distributed over the matrix addition, like this one, R times A plus R times B. First you can find R times A and R times B, and after adding them you can find this one. For example, like this one, we can find the same result, namely the first, this also can be found as 2 times A plus 2 times B according to the property. Let's find first 2A. We will get the same result, as you will see now. 2 times A is 8 minus 2, 0, 6, 10, 4, 2 times A, plus 2 times B, 2 times B, 2, 6, 2, 10, 2, 14. Addition of them will be 10, 4, 2, 16, 12, 18. Let's check. 10, 4 for the first column, we have the same first column. 2, 16 and 12, 18. Namely, we have the same result. We prove this one. And similarly, the matrix also can be distributed over the addition of numbers, as you can see, R times A plus R S times A. And we can change also the place of the parentheses. First we multiply the numbers, and then we use we apply the scalar multiplication with a matrix, and so on. So each quantity, each property in theorem 1 is verified by showing that the matrix on the left side has the same size as the matrix on the right, and that corresponding columns are equal. Namely, in each equality we have the same size for the result. Okay. So here we have an important operation, matrix operation, called matrix multiplication. Namely, how can we define the multiplication of two matrices? Do we have a definition for this one? We know the scalar multiplication, and we know the addition of them, also subtraction for two matrices, but we don't know yet the multiplication of two matrices. Namely, we don't have any number in this multiplication. All of them are matrices. So how can we define? So when a matrix B multiplies a vector x, it transforms x into the vector bx. We can define a transformation of x in this form, b times x. Namely, we multiply the matrix B by a vector x, as you can see. So x transforms into the vector bx. Okay. If this vector, as you can see graphically, we take x in the domain of the transformation, and the image of x will be the multiplication. As you can see, b times x. We know this definition from the previous chapter 1. So this vector, we obtain a vector, namely b is, for example, n by n matrix, and to define the product of them, x has to be n by 1 vector, and the multiplication of them, the product of them, will be let's say another vector. By cancelling the common number, we have n by 1 matrix. Okay, n by 1 matrix. So this vector is then multiplied in turn by a matrix A after obtaining the image of x under the transformation, which is the product of the matrix B and the vector x. So we multiply this vector, we obtain a vector here, by another matrix A, okay, by using the same definition. So therefore, A times the vector Bx is produced from x by a composition of mappings, the linear transformations. We define another transformation, y, A times y, okay, and instead of y we write the vector bx, so it becomes A times bx. Actually, we have the composition of two transformations here. For example, if we say another transformation, let's say bigger s, so it is the composition of, let's say for this one, t1, this one is t2, so this is the composition of t2 and t1. We have composition of two transformations, linear transformations. So our aim is to represent this composite mapping as multiplication by a single matrix denoted by A times B. The composition, namely S of x, is actually equal to A times bx, but we want to represent this composite mapping as multiplication by a single matrix instead of A and B, denoted by A times B, namely like this one, A times B x, A times bx. Instead of two linear transformations, as you can see, just we define a single transformation to obtain this one. Okay, therefore if A is n by n matrix, A is n by n matrix, B is n by p matrix, and x has p components, p times 1, and denote the columns of B by P1, B1, B2, blah blah, BP, and the entries in X by X1, blah blah, XP. Namely, the matrix B has the columns B1, B2, blah blah, BP. And X has the components X1, X2, blah blah, XP. So then the multiplication, the product of the matrix B and the vector X will be in this form, namely the linear combination of the columns of the matrix B with weights x1, x2, blah blah, xp, which are the components of the vector x, from the chapter 1. the product of the matrix B and namely the first transformation T1, and by the linearity of multiplication by A, namely we can distribute A in the addition over the addition A times x1 b1 blah blah A times xb bp. By the linearity we have linear transformation because so we have x1 can be written in front of the matrix A since it is a number. So we have the product of the matrix A and the vector b1, namely the first column of the matrix B, blah blah xp times the product of the matrix A and the vector bp, which is the last column of the matrix B. So the vector A times bx is a linear combination of the vectors ab1, ab2, blah blah, abp. Okay. Using the entries in x as weights, in matrix notation, this linear combination is written as namely A times bx, ab1, ab2, abp times x. As you can see, this linear combination is written in matrix notation. Okay. So therefore multiplication by this matrix transforms x into this one. Actually we have a single matrix here, as you can see. So this will be the product of two matrices. If A is n by n matrix and if B is n by p matrix with columns b1 blah blah bp, then the product is n by p matrix whose columns are written here. We have p columns and m rows. Shortly, when we want to find the product of two matrices, the number of columns of the first matrix has to be equal to the number of rows of the second matrix, n by p. So the result should be equal to n by p matrix by cancelling the common number m by p. Okay, and this is obtained from here. Okay, m by n by p, p by 1. Namely, when we multiply this one, so we obtain y n by 1 vector, n by 1 vector, and then we multiply this result by the matrix A. Namely, we use the first idea, namely we apply 2 times the linear transformation to obtain this one. So we have A times y, n by n, n by 1. So we have n by 1 vector z. Okay, n by 1 vector z. When we multiply this one. Okay, so the definition of two matrices will be in this form. A times the columns of the matrix B, AB1, AB2, blah blah, ABP. Multiplication of matrices corresponds to composition of linear transformations, as you can see. For example, compute the matrix, the product of matrices A and B, where A is 2 by 2 matrix and B is 2 by 3 matrix. So the number of column of the matrix A is equal to the number of rows of the matrix B. Therefore, we can define A times B, the multiplication of them. So this is written as A 2 by 2 times B 2 by 3 by cancelling the common number, this one. So the result will be 2 by 3 matrix. So we consider the columns of the matrix B, B1, B2, blah blah, B1, B2, B3, and the product of them, named A times B, you know, has the columns AB1, AB2 according to the definition, AB3. So AB1 is equal to the matrix A and the first column of the matrix B, and you know how you can compute this product. Let's check. The first column of the matrix A, namely 2 1 times 4, the first entry, plus 3 5 3 minus 5 times 1, so it is equal to 8 plus 3 becomes 11, 4 minus 5 becomes minus 1. Therefore we obtain this thing. Similarly you can obtain other products. So the columns of the product of two matrices will be like this one: 11 minus 1, 0 13, 21 minus 9. Okay, separately we find the columns of the product of the matrices given in the example, and we find the multiplication of them. So each column of A times B is a linear combination of the columns of A using weights from the corresponding column of B, as you can see. And we have a second way, for the matrix multiplication. I will give this way by solving an example by using this way, row column rule, for computing the matrix multiplication. We use the same matrices actually. A has the entries 2 3, 1 minus 5, and B has the entries 4 1 3 minus 2, 6 3. So the first definition says that the multiplication of them has the columns AB1, AB2 and AB3. This is the first way for finding the multiplication of two matrices. Okay, we know this result from in the example. And the second way, we apply row column rule. Namely, we write directly the matrices clearly: 2 3, 1 minus 5 times the matrix B. For 1 we apply the matrix multiplication, since the first one is 2 by 2 matrix and the second one is 2 by 3 matrix. Namely, we have the common number, which means that we can define the matrix multiplication for them: 2 6 3. So this is the second way, namely row column rule. Okay, first we use the first row of the first matrix, row, and we take the first column from the second one. Namely, we have row column rule. First row, first column. Then we obtain the first entry by multiplying the corresponding entries in the first row and in the first column for the corresponding matrices. So we have 2 times 4, 8, plus 3 times 1 is equal to 3. Namely, the first entry of the multiplication will be 11. Then we take the second column and first row for the first one. Now we take the second column. So we obtain the second entry in the first row, since we are taking the first row of the first one. Therefore, we find the entries in the first row for the multiplication. So we have 2 times 3 becomes 6, plus 3 minus times minus 2 becomes minus 6. And then we take the last one of the second matrix, and after the multiplication of the corresponding entries, we have 12 plus 9. 12 plus 9. So now we are taking the second row from the first one, and again we apply the similar operation. Therefore we obtain 4 minus 5 becomes minus 1, 3 plus 10 becomes 13, and 6 minus 15 becomes minus 9. Therefore we have 11 minus 1, 0, 13, and 21 minus 9. Okay, this is the multiplication of the matrices. Let's check. 11 minus 1, 0, 13, 21 minus 9. Namely, we have two ways for finding the multiplication of two matrices. You can use row column row like this one, or you can use the first way for finding the multiplication of two matrices. So we have another theorem after defining matrix multiplication. Namely, we will see properties of matrix multiplication in this theorem. Let A be an n by n matrix, and B and C have sizes for which the indicated sums and products are defined. We should write proper sizes for B and C to define matrix multiplication and addition, So we have associative law of multiplication, and we can change the order of the parentheses. First we can find B times C, and then we find the multiplication of A and the result of this multiplication. Or first we can find A times B, and then we multiply the result by C according to this order. And we have left distributive law for the matrix multiplication. We can distribute the matrix A over the addition of the matrices B and C. As you can see, they are equal. A times B plus A times C. First you can add the matrices, and then you can apply the matrix multiplication, or first you can find the multiplication of A and B and A and C, and then we can apply addition of the results. And also we have right distributive law. As you can see, we can distribute this matrix from the right side over the addition, and for any scalar r, we have these equalities, namely we can change the place of the number as we want, you see. And the order of matrices are not important when we have identity matrix for one of them. When we apply matrix multiplication, as you can see, the identity matrix times A is equal to itself. We consider the matrix A as n by n matrix. So when we multiply this matrix from the left side by the identity matrix, so it should be n by m identity matrix, okay, to get the common number. By cancelling, we obtain again n by m matrix, also the matrix A itself, since we have 1 for each entry on the main diagonal, and all entries are zeros except the main diagonal for the identity matrix. If we want to multiply a matrix from the right side by the identity matrix, so according to the size of the matrix A from the right side, so the size of the identity matrix should be n by n. It is a square matrix, you know. And so so the left to right order in products is critical because A times B and B times A are usually not the same, because the columns of A times B are linear combinations of the columns of A, whereas the columns of B times A are constructed from the columns of B. Since we have different columns for A times B and B times A, so generally we say A times B and B times A are not equal to each other. For example, we can see easily we have 2 by 2 matrix like the example, and B is 2 by 3 matrix. So we can define the multiplication of them. We have the common number, as you can see. So if we change the order of them, so we have 2 by 3 and A is 2 by 2 matrix. So it is not defined because you don't have the common number, namely the number of columns is not equal to the number of rows of the second one. Therefore B times A is not defined. A times B is defined. Therefore we have different results when we change the order of the matrices in product. So from here we understand easily A times B is not equal to B times A, because the right side is not defined, as you can see. So the position of the factors in the product is emphasized by saying that A is right multiplied by B, or that B is left multiplied by A. We should notice the order of the multiplication to get true result. If A times B is equal to B times A, if we have this equality, we say that A and B commute with one another. So we have important warnings here. In general, as I said, when we change the order, so they are not equal to each other. Okay, we don't have commutativity property for the matrix multiplication. And the cancellation laws do not hold for matrix multiplication. In other words, if you have this equality, so then it is not true in general B is equal to C, or we can cancel the matrix A. We can simplify A like this one when we talk about matrix multiplication, because we can have different matrices for B and C, but the multiplication can be equal to each other. Therefore, the cancellation laws do not hold for matrix multiplication. Namely, when we have this equality, A times B is equal to A times C, so we can have B is different from C. Okay, therefore we cannot simplify this one. If a product is the zero matrix, then you cannot conclude in general that either A is equal to zero matrix or B is equal to zero matrix. For example, A has the entries A has the entries 1 1 1 1, and B has the entries minus 1 1 minus 1 1. And let's multiply them. A times B, we can apply the matrix multiplication because the sizes are proper, 2 by 2, 2 by 2. We have the common number, so it is equal to, using the second way, namely row column operation. Row column operation, we take the first row of the first one and we take the first column of the second one, so we have minus 1 plus 1 0. Similarly, by taking the second column for the second entry, we have the same result, 0. 1 times minus 1 is minus 1, 1 times 1 is 1, plus 1 becomes 0. Similarly, minus 1 plus 1 0 for the next entry, and we have 0 for the last one. As you can see, A is not equal to the zero matrix, B is not equal to the zero matrix, but the multiplication of them is the zero matrix. This is not equal to the zero matrix, this is not equal to the zero matrix, but the multiplication of them is equal to zero matrix. Okay, this is the example for the third warning. So we conclude that in general, if A times B is equal to the zero matrix, so we may have matrices different from zero matrix. Powers of matrix. If A is an n by n matrix, namely we have square matrix, if k is a positive integer, then the product a to the power k denotes the product of key copies of A. As you can see, for example, A square is equal to the matrix multiplication of A by itself. Okay, A square. Simply, let's give an example. A has the entries 1, 2, 0, 1. We have 2 by 2 matrix, so we want to find A to the power 2. So it is A times A, actually, the product of two copies of A according to the definition, namely 1, 0, 2, 1 times 1, 0, 2, 1. And you can find easily it is equal to 1, 0, 4, 1. Okay, if A is non-zero matrix, if X is in Rn, X is a vector in Rn, namely we have n components for X, then A to the power k times X is the result of left multiplying X by A repeatedly k times. Okay, if k is equal to 0, then should be X itself. A to the power 0 will be identity matrix actually, or 1. So this one should be X itself. Therefore A0 is interpreted as the identity matrix, as I say. And another important matrix operation is called the transpose of a matrix. So far we have learned addition of matrices, scalar multiplication, matrix multiplication, and the power of a matrix. So now we learn the transpose of A, the transpose. Okay, they are matrix operations. So the transpose of A is the n by m matrix denoted by a transpose whose columns are formed from the corresponding rows of the matrix A. Theoretically, a matrix is given here, Aij m by n. So its transpose, the transpose of this matrix theoretically is written as, namely we change namely the rows of the first matrix will be the columns of the transpose matrix. Therefore we write Aji. Okay, the rows of this one will be the columns of the transpose. Therefore the size will be n by m. For example, generally, when we talk about 2 by 2 matrices, square matrices, A, B, C, D, so its transpose will be the first column has the entries of the first row for the given one. So we write AB and CD. Okay. The second row becomes the second column of the transpose, as you can see. Another example. Minus 5, 1, 0, 2, minus 3, 4. We have a 3 by 2 matrix. So the transpose of this matrix will be 2 by 3. So what is the first row? Minus 5, 2. So it becomes the first column. Minus 5, 2, 1, minus 3, 0, 4. 2 by 3 matrix. Okay. So of course we have basic properties of the transpose of the matrix A, like the previous operations. A and B denote matrices whose sizes are appropriate for the following sums and products. And we can define the product and sums for the matrices. When we apply the transpose operation 2 times for a given matrix, so we get itself, the matrix A itself. And the transpose can be distributed over the sum of 2 matrices. Okay, A plus B transpose is equal to A transpose plus B transpose. For any scalar, R times A transpose is equal to R times A transpose. Namely, we can write the number outside of the parentheses. And when we apply the transpose operation for the matrix multiplication, here this is important, we change the order of the matrices. As you can see, A times B transpose is equal to B transpose times A transpose. Okay, A times B transpose is equal to B transpose times A transpose. The transpose of a product of matrices equals to the product of their transposes in the reverse order, as we talk about. For example, let's prove the second property, namely, let's check whether we have the equality or not. A plus B transpose is equal to A transpose plus B transpose. So let's say A is n by n matrix, Aij n by n. So to define the sum, B is also n by n matrix, Bij n by n matrix to define the sum, and A plus B is equal to, the addition of the entries, Aij plus Bij n by n, and the transpose of the addition will be equal to, namely, we will have n by n matrix. We will change the meanings of the columns and rows. So this will be written as Aj plus Bji n by n. And let's look at the right side of this one, namely A transpose is equal to Aj n by n. So we should get the same result to say that this equality is valid, and B transpose is equal to Bji n by m. So the addition of them, A transpose plus B transpose, is equal to the addition of the corresponding entries, Aj plus Bji n by m. So we have the same result for them, which means that we have the second property. This is the proof of the second property. Similarly, you can prove other and properties written in theorem 3. Thank you very much for your listening.